All right. Well, it's my pleasure to it's just really an exciting time because biological treatment's been a number of years coming, and we're really getting really close to having a number of large systems installed, including one of ours. And I get the pleasure to talk about another novel subject. I didn't cooperate with the prior speaker to use that word, but we've got another novel one. I'm sure we got some more. What's pretty unique about our system is that we're using hydrogen gas as our electron donor. I'm going to talk about how we're doing that and what makes that pretty unique. Before I wanted to start, I didn't make a slide of this, but I thought it would be good to see who is APT Water, because that's the company I'm working with. We are a company that's been in existence since about 1980 in one part of the company and another part in mid-1990s. Our specialty is to make package systems, skids that we can deploy to a site. And it's a very applicable situation for the small water systems where a system would just, like an RO skid, for instance, we even make some RO skids. In this case, it would be an aeronite skid, but we also make advanced oxidation skids using hydrogen peroxide and ozone chemistry. But from a core technology or expertise, that's kind of the kind of company we are. But we also have an operations business where we have licensed treatment operators, and we run operable systems, operation systems at the City of Burbank, San Simeon, Redlands, and so we actually have treatment operators that we could deploy to operate systems too. So it's that package that we can bring to the table. Do I just hit forward? Okay, what is denitrification using hydrogen? I think we've seen this series of chemistry slides where we're using electron donors to take nitrate all the way to nitrogen gas. Goes through stepwise, but ends up with nitrogen gas, which evolves from the water, eventually degasses. In our case, we're using hydrogen as the electron donor. And why are we using hydrogen? Should say we'll talk about that. What is the proper conditions or why we're using hydrogen? In order for denitrification to occur, first you have to get the oxygen out. I think we heard some of that. For a biological system, it's important to have biomass retained in the system, usually as a biofilm, and so we're doing that as well. It's usually best to have neutral pH because the bacteria kind of like it that way. And the one nutrient that is pretty commonly needed in almost all of the biological systems is a little bit of phosphorus. And in our case, we use a little less phosphorus than the heterotrophic systems because one of the advantages that we'll talk about of hydrogen and using hydrogen is that they don't grow as fast, they don't grow as much biomass. It uses, and therefore if there's less biomass production, you need less phosphorus. And besides all those conditions, you need an electron donor. So we've heard a number of the other systems are using acetic acid as their electron donor, or it's an organic compound, soluble in water. And then you need to dose it in the front, and it dissolves in the water, and then it provides the electron donor for the bacteria that are going to be floating around or stuck on the surfaces there. In our case, we're using hydrogen gas, and the bacteria class is called autotrophs. May not be that interesting to differentiate in this audience, but they're just a different class of organizations. One of the major advantages, I'll just jump through some of these, of using hydrogen as for autotrophic bacteria, they grow, they use their carbon, they need carbon for their cells. They obtain that from the alkalinity in the water. There's usually enough alkalinity in the water. Almost always there's enough alkalinity in the water as bicarbonate for their cell growth. We don't need to add any. And so that's how they're growing, and they use that as for their energy source. In our case, we're using hydrogen, but the beauty about hydrogen is that you can make it on site as needed. You don't need to transport it to the site. Now I'm going to talk a little bit about how that's done at various scales. Since this focus is generally at the very small scale, the best way for that to be occurring is to make DI water and run an electrolysis system. And you can make hydrogen on site, and I'll show you some pictures of that in a minute. One of the major advantages of hydrogen, as opposed to dosing in a chemical, is that we don't need prior knowledge of how much nitrate is there. And it cannot be overdosed. In the case of adding acetate or ethanol, you need to dose a stoichiometric amount or a little bit more. You need to kind of know how much there is, or you're going to have an excess amount at the end to manage at the end. Can be managed, but you just have to have a good control system. In the case of hydrogen, there's no residual that needs to be removed, and therefore have to be treated afterwards from a excess BOD or TOC concentration after you use the hydrogen. And it's very easy to control. In the case of hydrogen, it's non-toxic, and we can't ignore, though, that it is flammable. And so with good design, engineering design principles, it can be handled just like gasoline can be handled, just like propane for your barbecue can be handled safely with proper engineering controls. And so that's just all about of doing it properly. An advantage of autotrophs is that they produce less biomass, about a third of what heterotrophs will make, and therefore there's less to be managed. And I think I'll just go to that. So what's at the core of this process? We're combining a number of relatively new technologies to provide a place for the organisms to thrive. And I'm going to show you kind of as we build up what the systems look like in a few minutes. But we're providing a way to feed biofilms in a pretty unique way using a membrane to transfer gas, in this case hydrogen, to that surface of the membrane. And so we're able to deliver hydrogen in a safe and efficient way just as needed to these biofilms. Okay, so a little history. Uh-oh, I didn't want it to do this. I wanted just to show them all. Okay, we've gone through a number of years of development of this from the original concepts almost 20 years ago now to licensing of the technology almost 10 years ago now, and then developing of various iterations of the process. We did a number of pilot testing, and as well as there was a question about Nsf certification. In this case, we're adding a new piece of equipment into a water treatment process. It needs to be Nsf 61 certified, and then it is. And we've had a number of testing systems, and just recently, in the last couple months, received the CDPH conditional acceptance. So we're one of the current ones that have been certified. We use the word aeronite. So what does aeronite stand for? It's really autotrophic reduction of, in this case, nitrate. So there are other compounds that can also be done in this same way. One of them is of some interest, which is hexavalent chromium, perchlorate, there's been some discussion about, and selenium. Those three classes of compounds, oxyanions, if you want to call them that, are all have the ability to be biologically reduced. And so those are other target applications. But of course, our talk today is about nitrate, so we're just going to focus on that. So how does the system work? We have a treated water that comes in contact with a reactor. I'm going to detail more about what's inside that reactor. We add hydrogen, which we can make on site. And we also are adding carbon dioxide. We add a little bit of carbon dioxide along with the hydrogen, both as pH moderation, because when one does denitrification, there is a pH change. And so a lot of waters, especially groundwaters, are relatively hard. And if we just allowed the pH to go wherever it was going to go, we would usually see some precipitation, some challenges with precipitation. So we need to manage that, and so we do that with CO2 addition. So from a consumable standpoint, carbon dioxide is one of them. Hydrogen, in that case, we don't have to bring that in. We just make it as needed. I think I said in words most of these things already. Hydrogen's made, carbon dioxide. We're feeding them. We feed them to the inside of a hollow fiber. And the outside of the hollow fiber is where the water is in contact with the biofilm, and that reduces the nitrate to nitrogen. After that, as we've heard already, there's the post-treatment parts of the process. And that would be the aeration, filtration, and disinfection. That would be similar to pretty much all of the technologies you're going to hear about from the biological standpoint. All of that's going to be pretty much similar. There's no magic difference between the downstream processes. A little bit more detail about what this device is. We're using hollow fibers to transmit gas. I brought some samples along. Ryan, if you don't mind, you could start at the back. I'll pass them around. These are much smaller hollow fibers than one might see for a water filtration membrane. Remember, we're not filtering water, we're transmitting gas. So these are about like fishing line, if you call it that. And they're tiny little pipes that we put hydrogen down the inside of that little pipe. Hydrogen being a very small molecule, kind of like helium, it will permeate. and it permeates through that fiber. It's a picture of the fiber, just a tiny little pipe. If you looked at it under a microscope, you can't see with your human eye that they're hollow. That hydrogen and CO2 permeates through the fiber, and on the outside of that grows a biofilm. And that's really what's happening there. So how do we develop that into an entire process? We take those hollow fibers, we weave it into a sheet, so it's like a fabric. Let's see if we take that fabric and we roll it onto a central core tube that's perforated. Water comes out of that perforated core tube, flows past the surfaces of that fabric, and the technical term is it gets slimy. And it's pretty much like a hot tub that you never put any treatment chemical in. It just gets real slimy, and that's the biofilm. The water's flowing across that. We put a spacer channel to provide a flow channel for the water to flow on, and the water transmits through this module in a spiral manner. We cap the ends. We pour a resin. We pour the whole module in a resin, shave it off very nicely, put a cap on the end. That's how you get hydrogen inside of those tiny little holes, because otherwise you might be wondering how you do that. So that's how you do that. Water is in the outside of that. What's transmitting across the fiber is hydrogen. So it's not plagued by the things that you might think of when you think of membrane filtration, like fouling. We're not stopping hydrogen from going through there. It's not water passing through that membrane. It's hydrogen. It's gas, and so that doesn't foul it from the standpoint of stopping the transmission of the important electron donor. Over time, and we do it about once a day, once every couple days, we do a sparging process to control excess biomass. And so we'll give it a shot of gas, and then that excess biomass will go with the water, and then we'll filter it downstream when we talk about the downstream parts of the process. This is a picture of what these modules look like. I didn't give you a physical scale of them. They're pretty large. They're much larger than RO modules. They're about 6 feet tall, taller than I am, about 1 foot in diameter. And we put them in a tank, submerged. This would be a picture of the inside of one of our test systems. And so there's a cap. That's an earlier version of a cap. We apply hydrogen to that cap, and then that's what provides hydrogen to the inside of those modules. It's gone through numbers of years in development. You can see the kind of list. It started out as pilot systems. One that's relatively important from the CDPH perspective, we did a pilot testing in Modesto or Grayson, small town outside of Modesto, and did a whole CDPH data collection, 30-day trial, and some testing there. And then on a pilot module, and then when we did the commercial module, the bottom line is our commercial system that we obtained the subsequent data that we used with the conditional acceptance that we just reviewed. In the case of the Modesto, you can see kind of some typical data. This is the average data from the 30 days of running. In this case, we measured it as N, so you multiply by 4.5 roughly. So I think it's around 70, 65 to 70 as nitrate. But what comes out is very much non-detect. And so some of the discussion earlier was about, well, what do you normally do in this case? Is that you take a portion of the stream, treat it to essentially non-detect or very low levels, blend around a fraction, and thereby increasing your real production rate. Might be twice what you have to. Treat half of it, blend half, for instance, in this case. And then you'd end up with 7 as N, 30 or so as nitrate, whatever that. We weren't looking for reductions of chromium and selenium, but we did see it in the data set. That led to a number of the draft conditions and then the later installation, which we installed in Rancho Cucamonga. It's down in San Bernardino County. And this is a graphic of that and then a picture of the actual installation. And this is a case where we put in a system late in 2011, started up 2012, and ran it throughout pretty much 2012 to obtain the conditional acceptance data. That's just to give you a feel for sizing, scale, depending on the audience. This is probably too big for some of the discussion today, but that well is around a 600 GPM system. This physical size is about half of that, about 300, and getting up to 400 GPM. And some of our later improvements go in. Some pictures of what it looks like, just to give you a real feel for what a system looks like. We build off-site a tank. This end is, inside of that tank is one compartment is an aeration chamber, so we're re-aerating the water. The 3 vessels on the end are media filters for the filtration part of the process. And then you can't see off-site, but there's some disinfection on another part of the process. But that gives you a feel for what a skid or a system might look like at the multi-hundred gallon a minute scale. From a process analyzer standpoint, and this kind of came up with Eugene's discussion, what's normally going to be required is some nitrate analyzers, turbidity for the compliance on the filtration, and then as well as a disinfection compliance. And so there's a number of online analyzers that are part of the package. Typical data going in at 70, less than 5, around 4 as a product target. So nitrate performance has been pretty well established. Wanted to show some pictures of what a smaller system looks like. This is a system that's around, of course it depends on the nitrate concentration, but it's just a typical field. This would be something that's around a 20 to 50 GPM kind of a scale. So this is a pretty simple system. There's some modules in a plastic tank. You can't see the whole tank, but you see the curvature of the tank. There's an aeration tank. You can kind of see the bubbling blue water in the back. Pair of media filters, and then there's some tankage that are relatively cheap, inexpensive plastic tanks, but that's the way that the system would be designed. You can see the silver item on the on the left. That's a hydrogen generator, and in that case, we take a little bit of the water. We have a little lab DI unit, makes deionizer, so it would run through a ion exchange, RO ion exchange to make a little bit of DI water, and you generate hydrogen on demand from water. And so that's the mechanism for the process. This was run at a site that I think the well capacity was 50 GPM. So the cycle, the well would turn on and off to fill the influent tank. And then we were just feeding out of that at the 10, 20 GPM, 30 GPM kind of range. So that's kind of what physically what it would look like. In this case, we rented 2 trailers or 2 Connex boxes and put a cover over it. So physically, you can picture that of what it would look like. So that would be useful to visualize what it would look like. We've already figured out how to do this from both off-site process control management. We run these off of a cell modem and an internet connection. You can control them with an iPhone app, and they'll send out an email if they have any alarms. And the data is collected on a minute frequency, or it could be faster, but we usually are running minute. We'll send that to a central data server. So we've got, I think we've run about 20 systems that, not all Aeronite, but 20 systems that are running off of cell modems and remote operation. So very conceivable to have numbers of these deployed and run from a centralized location. So we were asked to do some indicative costing, as I had mentioned to the prior speaker, and then I'll restate it. Much of the system is going to be independent. Cost-wise, is going to be independent of flow because you have instrumentation, process control, all those items. So really anything in the 1 to 50 GPM range is going to be in this capital range of around upper hundreds to upwards to maybe even 500K, which is right in the ballpark of what I think the 220, what you were looking at the similar systems. And then I changed the units. I think we heard months, and now we heard years. And then I used 1,000,000 gallons instead of 1,000 gallons, just to keep you guessing. Anyway, that's the values. I think they're right in the same ballpark. So what to walk away with? We're using naturally occurring indigenous bacteria. We don't have to seed. I didn't say anything about startup time. Usually we'll start seeing activity within days, and then you're going pretty much like gangbusters or full out within 4 weeks probably. And then we didn't talk about challenge testings, but the challenge testing involves shutting down and restarting. And generally what you find in those cases is that the bacteria are there and hungry and they're ready to go. And there are mechanisms to keep them happy and alive for 14 days or even longer if you want to. In our case, we have a very low biomass compared to a carbon dosing system. We're not managing an organic residual by a post-biological filter to take out any excess organic that was dosed in too high. We'll generate hydrogen. I mentioned at the low end, at the 50 GPM kind of range and less, it's very amenable to electrolysis, hydrogen generation via electrolysis. At the higher scales, in the hundreds of gallons a minute, 1,000 gallons a minute, the preferred mode that we will use is to use natural gas from the street, presuming it's in the street. It's not in the rural communities, but in most of the larger wells, it would be available in the street, and then we would make hydrogen with a small-scale steam methane reformer is the technology. But those are now becoming available. We're working on making one for ourselves, and it will physically be the size of a dorm refrigerator, kind of a size, or a large microwave. Not very big device, and it'll take natural gas from the street, make hydrogen on demand, and avoid the shipment and handling of electron donor other than that. I think those are the rest of the key things there. And thank you for your time and interest. Did I ruin the schedule?
Nobody's using comment cards, but are there any questions from the audience? Yes. Thank you.
Hi, David. Kim from Gallo Family Wineries. I just wanted to ask you about the hydrogen. How exactly is it regulating itself? Is it working on saturation or?
Okay. Actually, I didn't go into that, but it's this one work as well? Okay. The way it works is that if you have a membrane transmitting hydrogen, you have nothing on the other side. It's gonna diffuse across it based on a concentration difference or a partial pressure difference. Really, it's gonna be driven by concentration. What happens when bacteria grow a biofilm on the side is that they become a coating. They hinder the free transmission. And so what happens when the bacteria are presented with nitrate, they consume hydrogen at the surface of the membrane, which drives down the localized concentration right at that membrane, and then that drives more diffusion. And so there are cases where we've done this experimentally, where you're not telling the hydrogen control system or the bacteria to do anything. You're just putting in more nitrate. Throw in a handful of sodium nitrate, and the hydrogen level will just go like this. It'll just go up. Because they're pulling nitrate out of solution, because they're presented with more nitrate, they're going to demand more hydrogen. That locally reduces the hydrogen concentration at the surface of the membrane. Then that in turn drives more diffusion. So it's a chain reaction, if you will, and it self-regulates the hydrogen pull by how much nitrate is needed to be removed.
Hi, Jennifer Clary, Clean Water Action. I was wondering, with the contaminants you listed, those are the only ones it removes. I'm just wondering about common co-contaminants with nitrates, like arsenic and manganese. And the second question before you answer that is, what's the pH range that it functions at?
Well, the best pH range is generally in the 7 to 9 range, 7 to 8.5 range. The higher, we generally, as part of a design, we'll need to know the hardness of the water, alkalinity of the water, and we'll need to maintain the pH to make sure that we're not in precipitating conditions. But 7 to 9 is usually the happy zone. Oh, so since this is a biological reduction, we do get arsenic reduction, but generally it's going from 5 to 3, which isn't really doing the objective. So I wouldn't, we're going to see some, but it might not be. I wouldn't sell you one. Okay?
Other questions?
Uh-huh.
What about variable speed? A lot of people are using it, and then let's say it's my community.
Okay. I'm sorry, that's right. So you're in the summertime, you have a lot of people in the community and using water, and then in the wintertime you don't have very many people at all.
So, of course, we'd have to design a system for the worst case scenario. So we'd have to design it to handle the flow rate that would be needed at its peak capacity. So if it were low demand or it's on off, you'd be under using the full capacity in the winter months. There's not much around that. I think
Just as a follow, does it start up immediately then? in
well, if it were completely
variable
clean
flow?
a completely clean system on brand new modules takes, I think I might have mentioned, a few days before you'll start seeing activity, but it'll take a few weeks before you're really running at a design rate. But when you don't need the capacity, you can manage these systems so that you're kind of on low idle, if you will, and then it'll fire up. Because the same bacteria also remove DO, one of the strategies is to recycle aerated water. And in fact, we did that in one of our challenge testing, is just to recycle aerated water, because you can just run on DO for a while if you don't need water and you just want to keep them happy. So there are ways to keep things ready to go.
Aaron King from UC Davis. Do you have any idea about incomplete denitrification and what kind of production of nitrous oxides you're getting, or if any?
We haven't seen any. We have a good mass balance to show that N shows up. Well, let me see. We don't have nitrous oxide data. We have done some head space. We haven't seen it, but doesn't mean there's zero. But we haven't seen any. We do. One of the challenges of biological denitrification is you got to watch for nitrite. We heard that earlier, and so you'll get incomplete denitrification that stops at nitrite. You want to make sure that that's not happening. But generally, I think that's one of an advantage of doing treating part of the stream to low levels and blending around versus treating all the stream to half rate, or
Maybe you said this already, but what was the cost per household per month like?
Boy, I didn't do that math, so I don't know if I'd want to try and do it publicly in front of everybody, because I didn't divide it in those terms. Sorry. Yeah.
So what we're going to do after these 2 days of presentations is take all the technologies that you've been given, take the information we have, and do the math, so that there can be some comparisons using the information parameters that we gave the various vendors, and hopefully you can compare apples to apples. So, okay? So watch for that on the website. I think that if I don't break now, then you won't get a break. So I will resume promptly at 20 minutes to 3 o'clock. Thank you. Hello? We will resume. Welcome back. Yeah, if you could round them up. This is the tail end of the day. As you're taking your seats, I want to remind you that nobody's really followed this, but we do have question cards if you want to fill this out, or I'll just come to you. There are those. For those of you on the web, don't forget auditorium at calipa.ca.gov. At the back of the room, there are evaluation forms for those of you that will not be with us tomorrow. If you could please fill one out, they're at the back of the room, just to let us know how things went, what you thought of the presentations, how we did, whether we could have done anything differently. That is at the back, and we would appreciate it if you could fill that out. With that, let's go to the next presentation, utilization of a fluidized bed bioreactor for the treatment of nitrate-laden water to potable water. That's a mouthful. Thank you.
All right. Well, thank you very much, everyone, for attending the presentation and sticking around to the later part of the afternoon. My name is Todd Webster. I'm the Regional Vice President for Envirogen Technologies for the West Region. Just take a second to tell you about who Envirogen Technologies is. We're a company started in 1988. I joined them when I was a grad student back in '93 and have been with them ever since. And we've gone through Envirogen products, and then were bought by Shaw, but kept our Envirogen products and technology name. And then ultimately we're sold off, and we're in Envirogen Technologies under a company called Amplio Filtration. And we also specialize in reactor technologies, both biological and phys chem, including ion exchange technologies. So, you know, the saying always is when everything looks like, when all you have is a hammer, everything looks like a nail. And having multiple technologies in your quiver makes it really nice to be able to compare for clients, to be able to help them understand what technology may be better, bio or phys chem technology, again, ion exchange or coagulation filtration or biological. So, and then we also provide a service component as well, where we also operate all of these technologies that we sell for our clients. So that's also a benefit we provide. Well, today I'm here to talk about a number of things, and mostly about nitrate treatment in biological systems. We've heard some really good talks already. Eugene and others have given some talks about biological treatment in general, and then some more. We're getting a little bit more in this afternoon, specifically down into the detail of different technologies. I'm going to talk about a technology that I've been involved with since 1998, and really have spent the last 12 years of my career trying to get this technology built for drinking water treatment. And so it has culminated, you may have heard earlier, in a system that's now going into operation. And I'm going to give a little bit of background and detail on that particular system, but talk about the fluidized bed reactor in general. So we've talked in infinitum today. I've heard many, what are our choices for nitrate treatment? Ion exchange resin, it's a phase transfer, additional waste streams to treat in the brine, and then biological treatment. I just narrowed it down to those two for now, where it's a contaminant destruction technology, a minimal waste stream generation,